Hello, everyone, and welcome to today's SANS webcast, Modern Web Application Penetration Testing Part 2, Hash Length Extension Attacks. My name is Carol, author of SANS, and I will be moderating today's webcast. Today's featured speaker is Adrien de Beaupre, Principal SANS Instructor. If during the webcast you have any questions for our presenter, please enter them into the questions window located on the GoToWebinar interface at any time. Please note that this webcast is being recorded, and a copy of the slides and recording of this webcast will be available for viewing later today and can be found on the SANS registration page. And with that, I'd like to hand the webcast over to Adrien.
Thank you, Carol. Hello, everyone. My name is Adrien de Beaupre. As Carol mentioned, I'm an instructor with the SANS Institute. I'm also an author, co-author of one of the SANS courses that we'll be talking about today, which is 642, the Advanced Web Application Penetration Testing, Ethical Hacking, and Exploitation Techniques course. My co-author, Moses Frost, and I have tried to bring some of the more advanced and complicated attacks to you in this course and try to simplify them and explain them in a way that's understandable to most penetration testers. So there's a bit of a story behind this particular webcast. The story goes, I was giving 642, the class, to a bunch of students some years ago, and a friend of mine by the name of Ron was in class. And Ron came to me after class and said, you know, Adrien, there's something missing from the class. I said, okay, Ron, what's that? He goes, well, it's called a hash length extension attack. I said, well, Ron, that's very interesting. I've been looking at those. I think I should put them in the class. He goes, I agree. And there's a tool that you should use in your class. I said, wait, Ron, wait. You wrote that tool? He goes, yes, I did. So this is Ron Bowe's way of trying to ensure that his name is mentioned in essentially almost every SANS class in the Pentest curriculum is by approaching SANS instructors and writing content for their courses. He's done so in 560, the Network Penetration Testing class, 660, the Advanced Network Penetration class, 542, and now 642. So that being said, a bit of background as to why this content is now in the course for some years now. It's been updated and modernized since. And I'd like to talk to you about what a hash length extension attack is, what it means, and how it's performed. So first off, which algorithms are vulnerable? And the answer is almost all of them. MD4, MD5, RIP MD160, SHA0, SHA1, 256, 512, and Whirlpool. Okay, so that's a significant proportion of the hashes we use in modern applications. Some of them are deprecated. For example, MD4, MD5, SHA0, SHA1 are all deprecated, so we shouldn't use them anymore. And the question is, what is the vulnerability and what does it mean? So let's go into the background first. First, they all use something called the Merkle dam guard construction. This is a method of padding. Padding is required because the input to a hashing algorithm can vary in length. It can be any size. However, the output from a hashing algorithm is always a fixed size. For example, 512 bits. So how that works is, for a very small input, let's say, for example, we input 25 bits, there has to be a way to extend or pad, putting in additional information between 25 and the limit, in which case it may be 448 for a particular algorithm. So between 25 and 448, we have to put something. This is known as padding, and Merkle dam guard is a particular method of performing this padding for all of these hashing algorithms at the top of the slide. Now, again, Adrien, what's the point? Well, the point is there's two main methods to perform a check against something the server gives you and you give back. So, for example, if the server gives you a value you both know and a hash, it could be either a MAC, MAC, message authentication code, or a HMAC, or a third construct called a signature. I'm going to talk about the first two. So a message authentication code, imagine the server gives you something you both know, the name of a file you wish to download, download.png, and it gives you a hash. If you try and change the name of the file to myfile.png, presumably the hash no longer matches and the server will not let you download the second file, only the first one, download.png. Of the two methods to do so, MAC uses a secret we do not know and the value we do know, download.png, puts them together and then creates the hash, but we don't know the secret. The second method, called an HMAC, uses a key instead of concatenation, such that the key, also not known to us, like the secret, becomes part of the algorithm, and if we change the hash or change the file name, they will not match when the server recalculates. However, the first method I mentioned, MAC, without the H, is vulnerable to something called a hash length extension attack. And it deals with how Merkle-Damgard padding is performed and how hashing works. So we're going to have to dive fairly deep into how hashing works to understand how this particular attack works. Again, as a bit of background, this content is extracted from the 642 course. It's extracted primarily from day 3 content. Day 3 in 642 is an entire day, more than 6 hours of cryptographic attacks. And in fact, cryptography is so much fun, it actually spills into day 4, which is this bit of content here, from the beginning of day 4 of a 6-day class. Okay, so let's talk about how SHA1 works. SHA works in chunks of 512. So for example, if our input is the lowercase letters A, B, C, D, E, 6 bytes. In hexadecimal, that would be 61, 62, 63, 64, 65. Then the higher order bit is always switched to 1. That's, if you see in the bottom of the slide, right around here, there's an 8. So 80 means the highest order bit is turned to a 1. So 61, 62, 63, 65, 61, 62, 63, 64, 65, 80. Then all zeros out to 448. Then the last 64 bits is the overall size of the entire message. In this case, hexadecimal 28, which is 6 bytes. If we're only doing one round of hashing, this becomes the input to SHA1. Fair enough. What if our size is larger than 512? What happens is the first 512 bits become the first round, and the remainder become a second and possibly further rounds. Example, if we have 520 bits of input, the first 512 bits are used as the first round, then the 8 bits left over become the first 8 bits of the second round. High order bit is changed to 1, all zeros out to 448 of the second chunk, and then the size of 520 bits is converted into hexadecimal and put at the end. So this is how SHA1 fundamentally works. We're going to dive even deeper. SHA1 also uses another series of inputs. So getting back to our first round, if we only have one round, and it is A, B, C, D, E, that's 6 bytes, higher order bit turned to 1, all zeros out to 448 plus the size, that's one input. The next set of inputs are called the constants. The constants are always the same for the first round of SHA1. Then they run through the hashing algorithm and we have an output. If there's only one round, the output is the hash of the input. Now here's where the magic happens. For the second round, going back to our second example of 520 bits, our first round is loaded. The constants are brought in from the registers. The constants and the first 512 bits are run through the algorithm. and provide an output, the hash. Then we have the next 8 bits left over. So we have 8 bits, then higher order bit turned to 1, then the padding of zeros up to 448, then the overall size of 520 bits. Then the previous output of round 1 is loaded where the constants were. So the round 1 output is an input into round 2. Then our 512 bits of round 2 are loaded, and that produces a hash. So this is the magic, in that if the server gives us a hash, we could hypothetically load it into the constants, add something else afterwards, and rehash it. Now, the thing that we append, the length extension, matters, and it depends upon the input required for the application and what it is validating. Getting back to a file wish download, if, for example, we have download.png that we're allowed to download, they give us a hash, we then append at the end of download.png // myfile.png and input that. Without changing the hash, it'd be rejected. But what if we append, do a second round of hashing, taking their hash to replace the constants, our new appended value, recalculate and submit? Hypothetically, they might not give us the first file of download.png. They might give me the second file, myfile.png, depending upon how that server responds to that particular input. In this case, that directory traversal of .. might give us a second file. It also relates to the fact that the server, having given us the hash in the first place, might not correlate between, well, we gave this person the hash, we should remember it. Often the server will just give us that hash value and then recalculate it upon resubmission by ourselves and not remember that they have first sent us a different value. Okay, I think I see someone typing a question. Let's see if I can see the question. Okay. Nope, the question is from Carol. If I have any questions, please just submit them in the question window anytime. Okay, I just saw the question window going off. I'm going to put that back away. So let's get back to one round. If there is one round of hashing, server has a secret. Server takes the secret. After the secret appends the value we know, download.png, sends us the signature and the value download.png. We try and modify download.png to myfile.png, send it back. It doesn't match the hash, it fails. We try and modify the hash. We don't know the secret. We send it back. It fails. However, the hashlink extension attack with an MAC, a message authentication code, the way it works is, what if we take their hash, that's their first round of hashing. We replace the registers with the constants in the registers, recalculate with an append of .. myfile.png, and submit. Hypothetically, the server receives the hash, receives the value we send them, download.png / .. myfile.png, calculates it, gets the same results, and gives us a second file. Okay, so let's look a little bit deeper into MAC, Message Authentication Code. Let's assume that some file allows you to download, let's say, music after you purchase the file. I've not actually checked it, but I actually do subscribe to a music site that appears to, in fact, have this precise vulnerability. I'm never going to check because, of course, illegal, unethical, immoral. I do not have permission. So it appears as though they give me the name of the file I'm allowed to download with a hash. It appears as though if I change the file, the hash won't match. I can't download the second file. Fair enough. So there appears to be a secret I don't know as part of the hashing function. The reason I believe this is, if I download the file, look at the hash of the file, it does not match the hash. Look at the hash of the name of the file, does not match the hash. concatenate two together, hash that, does not match the hash. So therefore, to me, it appears as though there's some unknown value in that hash. We'll call it the secret. Assuming as well that the second value, the file name, the song I've purchased is the second value, let's assume they concatenate together, hash two together, and that is the hash they give to us. So we can see the file name, we know it. We can see the hash, we know it. We send one or the other back in modified, everything fails. So hypothetically, we should not be able to download any other file, in theory. Now, Flickr, which is part of Yahoo in September 2009, received an advisory that they were vulnerable. And to switch to the advisory for a sec. So this was the advisory sent to Yahoo Flickr at that time in September 2009. Flickr's API signature forgery vulnerability. It appeared as though, actually it was proven at the time, that in June 2009, they had many, many images and you could interact with Flickr through their API calls. They would give you a key that contained a shared secret that you did not know. To interact with the API, you had to take the key and create a signature for every function you wanted to call within the API. If the signature failed, it wouldn't work, but you didn't know what the key value was. As it turns out, without knowing the key, you create arbitrary new API calls with a signature that would pass a validation at their end. Now, the key aspect of this entire attack is you have to either know or guess the length of the key. So appending. This is where the magic occurs. They give us a hash. If we append a new value, it should fail. But let's assume we have the secret, the file name, some padding, and an append value. If we insert the correct number of values here, even without knowing the secret, it should pass MAC validation, so long as we leave enough room in the beginning for the secret. So let's see how this works. I take the file name, the padding, and the append, take their hash, load it in the registers as replacing the constants, hash again, and then submit. The beauty is the secret is already inside the hash they gave me. So when I submit to the server inserts the secret for me, puts in the known file name value, pads it out, sees our append, inserts the append, hashes that and goes, oh, the hash the user gave me and the hash that I have both match. Therefore, we've passed validation. We have a valid MAC. We'll give them what they asked for. Now here's, of course, the problem. How do I know or guess the length of the secret? Well, if I know the length of the secret, I just leave enough room. If I don't know the length of the secret, I have to brute force it. So I have to brute force the entire range of possible secret values. So at that time, I was looking around for an application that was vulnerable to the hashing extension attack, and I came across an application called Crypto My Goodness. Crypto My Goodness was written by some gentlemen at Trustwave some years ago. I believe they subsequently left the company, but I asked Trustwave permission to use Crypto My Goodness in the class, and they said yes. Great. At that time, Andrew, the person who wrote, I believe, the majority of this code, wrote on their blog the solution to challenge 1 and the solution to challenge 2. And I went through all 5 of them and solved them and went, well, challenge 5 is actually the one that's of interest to us because it appears to be a hash length extension attack. Challenge 1, I think, is padding Oracle, and 3 and 4, you'll have to figure out for yourself. Challenge 5, when I click on it, I see the screen to the right. I see algorithm and some links. When I click on the links, here's what's interesting. This is in Burp Suite. In the proxy history, I see algo equals SHA1 because I did in fact click on SHA1. I see file equals test because I clicked on test, and hash equals. What's interesting is that hash is not of the name test. And if you look at the contents in the response, hash is also not the contents of the file called test, and it appears to be the contents of a file. It's also not a concatenation of the name test and the file contents test hashed out. So my guess is there's something in the hash that I don't know what it is. Let's call it a secret that only the server knows. So let's also assume that the purpose of the exercise, going back to the previous slide, is to access Etsy password. Now, accessing Etsy password could be a number of different attacks. It could be a command injection. I'm going to assume it's actually a file inclusion. Getting to the next slide, when I click on challenge 5 and click on test, I'm going to assume they are including the contents of the file called test into the response. This appears to be the case by clicking on the other links where I see contents that appear to be a file. So let's argue that perhaps file equals test is the file name, and the contents of the file are then displayed in the response in the browser. And the hash is concatenation of the file name, in this case test, and a server secret value that we don't know. So enter into our hash extender. Hash extender was written by my friend Ron Bose, and it has a number of options we'll need to use. -D is for data. That is the data they give to us, in this case the value test. -S is the original signature. In the previous slide we saw it was called hash equals. So everything between DD03 and 100E at the end is for HTTP. -A is for whatever we wish to append. Now, getting into that for a sec, if I wish to append, if I know the name is test and I want to get it to somewhere else, I want to get to Etsy password, I may have to use two different techniques. One is called directory traversal, which is .. / usually about 9 or 10 times to escape out of the web root, arrive at the root of the web server, and then get down into Etsy password, which is the file inclusion. So my data to append will be those .. Etsy password. -F for the hash format will be SHA1. -L in this case, if I know the length of the secret, I put it in. If I don't know, there's a --min and a --max to do an entire range of, let's say, between 10 and 40 characters. And if you wish, you can also have hash extender URL encode the output format. In this case, --out-format equals HTML. Will URL encode it for us? If we're using Beaupre or other interception proxies, usually they'll do the URL encoding for us. We don't have to do it separately. But if you're using curl or some other utilities, you may have to. Just see the chat window going off for me again. Copies of slides and recordings will be available for you, and yes, it will. Sorry. So this is our syntax for hash extender. I did hash extender every value between 10 and 40. I ran it through the tool called Intruder. And Intruder, doing both the file name and the hash value, came back and at round 25 gave me a 200 OK. For every other insertion, it gave me a 404 with a size of 1464 bytes. At number 25, it gave me 200 OK at 2,773 bytes. Two very clear differences. Looking at the contents, we see test, then a strange character, a number of .. and then the contents of Etsy password. Since I started at 10 and ended at 40, you would think I'd end up at number 24 to get to 34. But what happens is Beaupre Intruder always has a baseline run of an unmodified request. So number 1 is actually the baseline, and number 25 would be 34 bytes. In this case, we've discovered by brute forcing that 34 bytes is in fact the answer for this particular solution, because it did not tell us how many bytes to go in for the secret. I discussed all of this on the SANS blog. The SANS blog's been reorganized slightly recently. So Modern Web Application Penetration Part 2, hash extension attacks, has been moved from the original Pentas blog to, they've merged all the SANS blogs together. So I discussed this at that time, again with permission from TrustWave to discuss their application. Now, you're thinking, Adrien, let's see code, let's see demo. Now, the thing about demo is interesting, is I always ask them to send me a virgin goat. And of course, they never do. They're like, Adrien, what on earth do you need a virgin goat for? Well, of course, the virgin goat requirement is to sacrifice to the demo gods, because demos do not always work. However, let's try demo. So here we see the application called Crypto My Goodness. And it's in a directory installed on my server. There's Crypto My Goodness, in a directory called CTF. And we see challenge 1, 2, 3, 4, and 5. So challenge number 5 is the interesting one in this particular case. Click on challenge 5, algorithm, SHA1, save, then click on test. I'm going to theorize that this is a test, is the contents of the file test. Pictures, same idea. Links, same idea. Home, same idea. Some lovely poetry. And hello is hello world. So let's see what this looks like in Beaupre. Going into the Beaupre proxy history, we see here is the interesting content. Algo is SHA1, file equals test, and hash equals. Notice that no matter how many times I click on this particular file, hash always remains the same. So there's no additional timing or other content in there. You'll notice that same value from the slides, DD03 through 100E. So what's of interest here is, what if I take that value and this transaction send it to a part of Beaupre called repeater? I'll hit go for replay attack, and we see down here, this is a test. If I change the file name to something else, we know there's another one called hello, and go, and it says not found. But we know hello is there. We go back here, go to my goodness, click on hello, go back to the proxy log. We know that hello is there, but hello is a different hash. So if we not submit the correct hash for hello, we do not get to see the file. I'm going to send him to repeater, and it go for a baseline, and we see hello world. But if we change the hash, let's just arbitrarily change some of the hash values here to FF, and it go. We see the relationship between the hash value and the word hello is significant. If you change the file name, it does not work. If you change the hash, it does not work. So we want to bypass this to see the contents setsy password right there. In this case, we know the value is 34. For file equals test. Let's get back to a valid baseline. It's recommended in many forms of penetration testing with web apps to always start with a valid baseline. This is a test. I'm going to show you here the syntax. This is the syntax to start at 10 and go to 40. So the mentioned -F is for format, in this case SHA1. Data is unchanged, in this case test. -S is a signature given to us by the server. the value is DD03 through 100E. -- append, this is the actual attack, right? It's the directory traversal with sufficient / slashes to escape all the way out of the web root and then grab the contents of etc password. I'm going to say the minimum is 10, the maximum is 40. Do it in URL encoding and send it as a table. Now, if I do this exact syntax, it'll give me a file called signaturesandstrings.out in this directory. So I've downloaded hash extender, extracted it, and compiled it. And I'm going to do -n2 of signatures and strings. And of course, I typoed it. There we go, demo dots. So this, for example, is the first signature. And this is the first append. This is the second signature. This is the second append. And basically, it's just extending out, going one character at a time between 10 and 40, trying to get the correct value for the insertion. Now, having played around with this quite a bit, I happen to know the correct value is 34. I can also cheat with the source code. So hash extender, format SHA1, data test, signature, the original, -- append, L34, lowercase l, -- format equals HTML, -- table. So this is where we're going to do the actual insertion. It gives me a SHA1. I'm going to copy that. Going into repeater, I'm going to replace their hash with the hash given to me by hash extender. I'm also going to replace the value test. Now, remember this guy? %80, that's padding, right? All the way out to the / slashes. And there is the size, right? Then %2E, %2E, %2F, 2E, 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 2F, that's on the slash, all the way out to /etc/password. And copy that value here and put it in here instead of the word test. There you go. And it says, well, I tried to get it to password. It didn't work. And here we see test, unprintable character, 0, that's the padding, and then / etc password, the file name, and then the contents of etc password from the server inserted into the code of the response from the server, thus proving that algo is SHA1, which we knew. File equals test was in fact the name of a file name, and the hash was indeed a MAC, where the server secret was prepended, and we could take the hash they gave us, rehash it with an append value, and reinsert it. So long as we left enough room for the secret to be prepended by the server, we bypass the MAC or Message Authentication Code check from that server. Let's see, how am I doing for time? Oh, wow, I have lots of time. I only used up like half the time. So that's actually effectively the end of the presentation. The content in the course 642 is slightly more extensive, and we have a different exercise other than Crypto My Goodness, also written by my friend Ron Bose. Ron's a bit of an overachiever. He and a friend of his wrote their own custom hashing algorithm that was in fact vulnerable to hash extension attacks for a B-Sides in San Francisco, and gave that to them as their CTF one year, which meant that you had to download their custom hashing algorithm, basically decompile it and reverse engineer it to discover the hashing algorithm, the hash extension attack, and then use some different tool to actually recreate it, because the hash extender does not support that custom hashing algorithm that they wrote. It's like, wow, Ron, how to make this all look bad. If Ron, if you're listening, hi, how are you doing? Known Ron back since when he lived in Canada. He invited me out to lovely Western Canada to go to the B-sides where it was snowing. And it was quite chilly. So at this point in time, this is hash-link extension attacks. This is a modern attack against modern applications that implement cryptographic and hopefully secure methods. The MAC method I described is not cryptographically secure. One question that often comes up in class is, well, how often do I see cryptography be interesting in web applications? And the answer is almost always. And the findings are almost always very interesting, very critical, very high findings. One of the other themes of 642 is often attacks must be put together. For example, in this one we saw there was the hash-link extension attack, the directory traversal, // and a file inclusion. All three techniques were required to pull off the objective of grabbing at the password. It is not unusual in many attacks these days. So I'm done talking. That was hash-link extension attacks in a nutshell. Are there any questions? And please feel free.
All right, that great presentation. I do see that someone has submitted a question. However, if anyone else has a question for our presenter, please enter it into the questions window now. Our first question asks, how would someone identify an app that has been attacked via these methods?
You mean from a forensic point of view? The answer would be an incredibly large number of abnormal inputs. For example, the Intruder run that I would have done would have shown at least 30 or 40 abnormal inputs that should have caused some form of error to occur server-side inside the application, if I understand your question from the forensic point of view.
They said yes, that's correct.
Mm-hmm.
All right.
I can mention further that most applications do not log this type of activity. And they should.
All right, that's all the questions I see that have been submitted. Do you have any closing thoughts you'd like to share?
Please do come out and see us for 642 or at any SANS function. Myself and Moses are always around. If you're interested in taking the class, please let us know. If you have any questions, my email and Twitter are on the slide that you should see now. We are currently going through a massive rewrite of 642. So if you have taken the content in the past, look for a brand new version of the course later on this year, probably around September or October. And we're always open to ideas and questions. Thank you very much.
All right, and Adrien, we did have one more submitted. It says, hello, Adrien. I see you are still using Beaupre 1.7. What are your thoughts on 2.0?
Okay, so one, I don't like 2. That's a personal thing. I'm still stuck at 1.7 because I like it better. They're starting to get to the point where I have to switch to 2, so I'll have to learn 2. The other thing is all my slides in my class are written for 1.7, so I'm going to have to switch those. So 1, I have to get used to 2. I haven't got used to it yet. And 2, I have to switch all my slides, which I've not yet done so. So I think 2.x is getting stable now, and I believe it's no longer in beta. Yes, it is. It's no longer in beta. I double checked a couple weeks ago, but I've not gotten used to it yet. Does that answer the question?
All right, thanks. We've got a couple more questions. Can you preview what's coming in 642?
So can I preview
what is coming in 642?
Yes. Much more REST and Open API and Swagger, much less SOAP, much less of the older attacks, much more SAML, much more OpenID, much more OAuth 1 and 2, much more crypto. So all of the content that was inserted when I took over the course 5 years ago is going to be scrapped and rewritten from scratch. All the brand new content that's less than 5 years old is going to remain. So day 1, complete rewrite. Day 2 is frameworks. Day 3 is crypto, more crypto. Day 4, Java and Flash are going to drop. Much more HTML5. A lot more WebSockets, much more HTTP2, HTTP3 now. A lot more rests, a lot more swagger. Day 5, a lot more pivoting and pillaging. And day 6, brand new CTF. So look for half the course is going to be rewritten in the next 6 months.
All right, thanks. Adrien, if you could expand your questions window, I put one in there. It's a web page that's not accessible. Can we access it? I thought it might be best if you took a look at what the web page was.
So I can't actually see the question, or can I? Can I see the questions? I can't see the chat.
I think in the questions window, but I can, you know what? I can also send it through chat.
Oh no, so that's an internal website inside the course. If you have taken the course, you can download the VMs. If you have not taken the course, those are internal to the website, internal to the course. So if you take the course from me, you can get the app.
All right, thanks. And one more. When will the new version of the class be available on demand?
Usually it's about 2 months later. So I believe they're going to record me in Baltimore, and I think that's in late August, early September. So usually it's about 2 months after that, if I understand their timelines correctly.
All right, thanks. Well, that's all we have for today. Thank you so much. Oh, Baltimore says Baltimore is early September. She says, okay.
Is it really? Okay, yeah. That's my memory.
Well, yeah. Someone's got to get.
Memory's the second thing to go. Can't remember the first one.
All right, great. Well, thanks so much, Adrien, for your great presentation, which helps bring this content to the SANS community. To our audience, we greatly appreciate you listening in. For a schedule of all upcoming and archived SANS webcasts, including this one, please visit sans.org/webcasts. Until next time, take care, and we hope to have you back again for the next SANS webcast.
Awesome. Thanks, all.